Hello and welcome to Lecture 5 of Electric Fields in Phys 1204. Get ready for lots of integrals because we're doing fields due to charge distributions in this lecture. I mentioned in an earlier lecture that we would need this idea of charge density, and so let me just review the idea quickly and establish some notation. So you are hopefully familiar with the idea of mass density, where we have some mass, and it is contained in some volume V, and the mass density would just be the ratio of m over v. Well, similarly, if we have some charge Q, which is distributed throughout some volume of, say, a material, then we would have a volume charge density. And we'll use the symbol rho sub E for it, just like we often use the symbol rho for mass density. Note, this is not a P. This is the Greek letter rho. It's the Greek letter that says However, you know that when we rub objects together to charge them, the charge ends up on the surface, not distributed throughout the volume, and certainly in an insulator it will never then flow inside the object and become distributed through the volume. We'll also see that in conductors the charge almost always sits on the surface. And so volume charge density is actually not so useful very often. What we need instead is surface charge density, where we take the amount of charge on the object and divide it by the surface area of the object. And so this is a little bit more similar to a population density, right? How many people there are per square kilometer. This would be how many coulombs there are per square meter. But also, often we are talking about long, thin objects with charge distributed over them, and when we do so, it's often useful to talk in terms of a linear charge density, which is just the charge per unit length. I went through much of the idea of how to get the electric field due to a charge distribution in an earlier lecture, so let me recap it and establish some notation as I go. The idea is that we imagine breaking the object into bits, and now we treat each bit as a particle. And when I say that, I mean that now we define the point P where we want to know the field, and for each bit we can say that the field that it produces there can be found from our usual expression for the field due to a charged particle, where we're saying that this bit has some delta Qi as the charge on it, and so we get some delta Ei, which is the field due to it. And I'll just note that this I is an index, where we're saying this is the ith bit. We can imagine numbering all the bits, 1, 2, 3, 4, 5, 6, and so on, although most often we only do this conceptually. We don't actually go through the process of assigning a number to each bit. We then think of summing up all the contributions due to all of the bits, and that would be our total field at the point that we're interested in, where we note that that is a vector sum. However, also note that it's only approximate, because we've used the expression for a point particle field, even though these bits are not point particles, they're finite chunks of material. And so, strictly speaking, this isn't quite correct as the field due to each bit. And so when we sum them up, we don't quite get the exact field at the point we're interested in. But we can always take smaller and smaller bits, and the approximation will get better and better. Now, we don't actually take smaller and smaller bits, that's just the inspiration for what we actually do, which is that we take the limit as the size of these bits goes to 0. And that gives us an exact expression for the E field. Formally, when you take a sum and you take a limit as the pieces of the sum go to 0 and you go to an infinite number of pieces of the sum, that turns your sum into an integral. And I will note that there are some notationally important things going on here. We were summing over a discrete number of bits that we could index with some index I. And so this I was labeling each piece and the R vector associated with each piece. But now we're going from a discrete sum where we can label each piece with a number to a continuous integral, and so those labels disappear. Delta qi becomes dq, in other words, we're integrating with respect to q, and the I in the R is disappearing because we're now just talking about some continuously variable vector that can point from any point on the object to our point P. Note, however, you probably have no idea how to do an integral like this. You're used to situations where you're integrating along some axis, and now we're imagining integrating over a whole surface, perhaps. Don't worry, I'll show you in examples how you actually do this. The first example I'm going to do is the field due to a thin rod, and I should explain what I mean by thin. I mean a rod that is so thin that we can ignore its thickness. Or equivalently, we're looking at the field at a point P that is so far away from the rod that the thickness of the rod is very small compared to the distance that we're looking from the rod. And I'm going to say that we're looking at a point that is perpendicular out from the middle of the rod, so that's a special case. Now, the first thing you should always do when you're trying to figure out the field due to a charge distribution is draw the situation and set some axes. So I've chosen my axes so the origin is at the midpoint of the rod and the rod is lying along the y-axis. And the next thing you should do is choose an arbitrary piece of the rod. So I'm imagining that I'm breaking the rod up into many pieces, and here's one of the pieces, and I've picked an arbitrary one. Don't pick a special one like at the very middle or whatever, because you're going to try and build an expression for the electric field due to each piece, and your expression has to apply no matter what piece you're talking about. So here's a piece that I'll call delta qi. And one thing that's going to be of interest is where it is. So it is at a value of y that I will call yi, the y value of the ith piece. And something we know we're going to want is the vector that points from delta qi to the point P where we're determining the charge. So there is the vector RIP. And we know that the field due to delta qi must be k delta qi, where that is the amount of charge on that piece, over RIP squared r hat IP. Now the next thing to notice is that we have a fair bit of symmetry because we're looking at a point that is perpendicular out from the very middle of the rod. And in particular, what that means is that if we think about this E field due to that ith piece, delta qi, so there's that little chunk of E field, then note that there's always going to be another piece the same distance away over on the other side of the rod that's going to produce an E field like so. And what you can see is that the y components will cancel. So we already know that the total E field is going to point straight in the x direction. All the y components are going to cancel. And so there's actually no point calculating the y components because they're all going to go away. So we might as well restrict ourselves to the x components. So in particular, think about how we get the x components. All right, delta EI gets all of its vector character from RIP. And that is going to be RIPX I hat plus RIPY j hat all divided by RIP. And so in particular, we can see that if all we care about are the x components, because we already know that the y components all cancel, then that's going to come from this. And so in fact, what we want is, so to proceed, we need the RIP vector so that we can get its magnitude and we can get its x component. And I'm going to have you do that part. So as usual, if you're in the course and you're doing this through Moodle, then Moodle will ask you this question. Even if you aren't, you should try and come up with an answer to it before you go on to the next part of the video lecture.